Oh no, yeah, I'm recording, no problem. Okay, so share this. Okay, so this is the straightforward approach to interface devices with the CPU, which is called pulling. You pull the devices whenever, for every period of time, you pull the devices. You ask the devices whether they want to use the resources of the CPU, whether they want to be serviced by the CPU. It is not efficient in terms of wasting resources. It's not efficient in terms of delaying the service. However, they are simple to implement. You simply write some sort of code here to check, to communicate with the devices and ask them if they want resources or not. Okay, now, in order to address these issues related to pulling, the other way to interface with these devices is simply called interrupts. And the basic idea in interrupts is to have these devices connected to the microcontroller, device 1, device 2, device 3, whatever number of devices, and you have your main program that does certain tasks. And one of these tasks effectively is to service these devices. For example, if they are input devices, we want to read from them if they have data to be sent. In the other approach, we have the main program, which executes the repeated tasks, the tasks that I repeat. And whenever any of these devices wants to use the resources of the CPU, basically it sends a request, not data. It sends a request, which we call an interrupt request, which means it interrupts the execution of the main program. For example, let's assume that the interrupt request arrived when the CPU was executing this statement or this line of code. So what will happen when the CPU finishes this line of code, it will notice that some device, whether it is inside or outside the microcontroller, is requesting to use its resources. So what will happen, it will stop executing the main program and it will divert the execution of the program to another place where there is a special code that is loaded in memory in order to service this request, in order to service this interrupt request. So the code is executed. In our simple example, this code will be responsible to determine that device 1 has requested the CPU to pay attention to it because, for example, it has data to be read. It has some value to be read. So it will execute some code that will does this. It will do this. It will check which devices has interrupted the CPU and what service to be provided to this device. If it is an input device, output device, what type, depending on what the type of device and so on. So once it finishes servicing the device, it will go back and resume the main program, the execution of the main program. So this is more efficient because we don't have to waste time in pulling the devices, in asking the devices whether they want to use the resources of the CPU or not. And they provide, this approach provides a more responsive operation, because once we finish the current instruction, the CPU notices that there is an interrupt request. There is a request to interrupt the CPU, so it will service it as soon as it finishes the current instruction. So this is called interrupt approach. This is the interrupt approach in This is the interrupt approach in to interface devices, in which we have almost real-time response, because we will respond as soon as we will receive the request. In this case, we don't have to pull the devices every other time, so it saves resources. It basically saves the resources of the CPU. It saves the resources of the CPU. So these are the advantages of interrupts over the pulling approach, which are basically just the opposite. We save the resources, we provide almost near real-time response to the request. However, there is nothing free. If you want to use interrupts, you need to find a way to implement this mechanism, which is diverting the program execution when you receive an interrupt request. And this requires additional hardware and inside the microcontroller requires additional instructions or modification in the instruction set architecture in order to support this. You need additional hardware here to monitor the requests, to see whether a request has arrived or not, and then based on that to notify the CPU. So the disadvantage, the only disadvantage here is additional hardware and complexity of software, because we need to be aware of this. How is this done? So this is the basic idea of interrupts, which is basically you allow devices to interrupt the CPU while it is executing some program. And this interrupt request will be serviced by the CPU by executing a special piece of code that I write. It is not written for me. I write because I know what these devices, what type of service these devices require. So this is the main program. This is usually the main program. And this is the piece of code that services the interrupt requests. That's why we call this the interrupt service routine. Interrupt service routine, which is similar to subroutines. If you remember when we discussed the subroutine, this drawing is very similar to what we had when we discussed the subroutine. Basically, when you call a subroutine, you change the flow of the program to another place in memory where you have the subroutine loaded, you execute the subroutine, then you go back. However, the stimulus here is not a call instruction. There is no call instruction here. There is an instruction, normal instruction, but what triggers this change in the program flow is basically a hardware event, which is an interrupt request from some device that is connected to the microcontroller. So here we introduced a new terminology. This is called the interrupt service routine. Basically, it is the routine or the subroutine that contains the code to service the interrupt request or requests from different devices. So again, what causes this flow change in the program is basically the arrival of an interrupt request from any source, from any interrupt source that is available in the microcontroller. And this will result in executing the interrupt service routine. And once we finish, we go back to the main program by executing a special instruction, which is similar to what we did in the subroutines where we had return from subroutine. Here we have RTI instruction in XCA12, RTI, return from interrupt, So this is the basic idea of interrupts. It is an approach that is used to interface devices to the CPU, whether this CPU is a standalone CPU or it is a CPU inside the microcontroller. All right. Now, the details of how this is implemented varies from one microcontroller to another. For example, what type of interrupts are supported, how many interrupt sources are supported, how to return from the interrupt service routine, where to load the interrupt service routine. These issues and other issues vary from one microcontroller to another, from one CPU to another. We will consider probably next time how this is implemented in the HCS12 microcontroller. Okay, any question? All right, no questions. So, usually microcontrollers, they come or they support different types of interrupts, depending different type and different number of interrupt sources depending on their complexity and model and the number of peripheral devices that are connected with the or integrated within the microcontroller. So if we talk, let's talk in general. If we have a microcontroller, this microcontroller has a CPU, and usually this CPU is, or this microcontroller has different devices, peripheral devices. So this is device 1, device 2, device 3. This could be a serial communication. This could be analog to digital converter. This could be a CAN, controller area network peripheral device. There are ports. There are pins that are for this microcontroller. So usually there is what we call an interrupt circuit. This is an interrupt circuit in which all interrupt requests go to this interrupt circuit, and this circuit, it could be inside the CPU or it could be outside the CPU in the microcontrollers, will send an interrupt request the CPU if any of these resources or sources generate an interrupt request. Now, the interrupt request might not be only from the inside, it might come from some outside, from source that is outside. For example, you may have one of the pins that can be configured to interrupt the microcontroller, for example, on the rising edge or on the falling edge. For example, this pin, whenever it sees a rising edge, it can interrupt the CPU. So the CPU will halt the execution of the current program and diverts to a special place where the interrupt service routine of this source is loaded. If this source generates an interrupt request, it can interrupt the microcontroller, the CPU, where the CPU will halt the execution and divert to the place where we can find the interrupt service routine associated with this source. So the sources of interrupts might be from inside the microcontroller, might be from outside the microcontroller. They could, their number varies depending on the number of integrated peripheral devices. For the output sources, usually they are associated with pins. For example, you may have 4 pins that can be configured to interrupt the microcontroller on a rising edge, or whenever they see a low value, low level, or whenever they see a high level. So all of this is usually configurable, how to define when the interrupt occurs. So this is actually one classification of interrupts. Some interrupt sources might be internal, some interrupt sources might be external to the microcontroller. Another way to classify interrupts is based on maskability. So some interrupts are maskable, while some interrupts are non-maskable. And by maskable, we mean that the interrupt can be masked. In other words, it can be covered, it can be ignored, or it can be enabled or disabled. So we may have many sources of interrupts inside the microcontroller, and we are not using all of these interrupt sources. So we just keep them disabled, for example, and we just enable whatever sources that we are working with or dealing with. So in this case, we are working with what we call maskable interrupts, interrupts that we can mask, interrupts that we can cover, interrupts we can enable or disable. For non-maskable interrupts, these interrupts cannot be disabled. They are always enabled. So whenever an interrupt request from this non-maskable interrupt source arrives to the CPU, it will service this interrupt request. And our microcontroller has both types. It has some of the interrupt sources are maskable, while some interrupt sources are not maskable. You don't have control over them. You cannot disable these interrupt sources, and we will discuss them next time. Okay, so this is the basic idea of interrupts. This is like a basic definition of interrupt. An interrupt is basically a hardware or a special event that requires the CPU to stop normal program execution, and perform some service related to the event. And basically performing this special service or some service is basically done by executing a special piece of code that we call interrupt service routine that is related to that source. And this is very similar to what I had on the board earlier. This is kind of, also I talked about it, functions of interrupts or advantages of the interrupts. They can be, to coordinate the interfacing between CPU and devices, and at the same time, preventing the CPU from being tied up. In other words, saving the CPU resources, reminding the CPU to performing some routine task, as we will see later when we talk about timers. Most microcontrollers, they come integrated with built-in timers that can be configured to interrupt the CPU at every certain amount of time. So you can use them to remind the CPU to do specific tasks every certain amount of time. Okay, again, we'll end the meeting in 10 minutes. We are almost done. Another thing here, I just talked about it, interrupt maskability. As we said, there are maskable interrupts and there are non-maskable interrupts. And how to enable and disable maskable interrupts, we will see later that different interrupt sources have special control registers. Okay, in which there is usually one bit that is responsible for enabling or disabling this interrupt source. So basically, usually there is a bit, an enable bit inside some register that is related to this interrupt source, and through that bit we can disable or enable the excuse me the interrupt. Another thing related to the interrupts is the priority of the interrupts, and this is very important when the CPU or the microcontroller may receive interrupt requests from multiple sources, which is the case of our microcontroller because we have too many interrupt sources. For example, we have the CPU inside the microcontroller. It may receive an interrupt request from multiple sources at the same time. So the question is, the CPU will notice that there is outstanding interrupt request or requests. So it will stop the execution of the current program and it will pay attention to the interrupts. Now it will find 3 requests, let's say. Which request to service first? This is called the interrupt priority. And this priority is usually defined in a certain way, either at the hardware level or at the software level, depending on the microcontroller. In our case, it is almost hardware defined. In other words, it is already defined that, for example, if we have 3 sources, that source 3 has higher priority than 1, and 1 has higher priority than 2. So in this case, it will service the interrupt from 3, then from 1, then from 2. Or we can change this order in software, as we will see later. In other words, we can override the hardware-defined interrupt priority. Okay, here is just the steps that usually happen when an interrupt request arrives to the CPU. Basically, the interrupt service cycle includes saving the program counter value in the stack. And why do we need that? Because we need, once we finish executing the interrupt service routine, we want to go back to the main program, similar to what we had in the subroutine, normal subroutines. So we need to save the program counter in the stack. And the program counter, essentially, when it is saved now, it contains the address of the next instruction that we finish executing during the arrival of the interrupt request. Then saving the CPU status, which is defined by the registers. So in our case, usually when an interrupt request arrives, the program counter is pushed to the stack. The registers A, B, X, Y, stack pointer, all of them are pushed automatically to the stack. You don't have to push them. They are pushed automatically in response to the arrival of, or to starting to service the interrupt request. Identify the source of interrupt. So we need to know which device, which source of interrupt initiated the request. Then we need to know where is the interrupt service routine is located for that source, because device 1 may have different interrupt service routine than device 3, than device 2, and they are located at different places in the memory. So we need to know where the interrupt service routine is loaded. Then we start executing the interrupt service routine. Then before we coming back, we need to restore the CPU status and the program counter. Then we resume the execution of the main program. So all of this is done during this cycle. Here we push the program counter, the registers to the stack. We load the address of the interrupt service routine in the program counter. We execute the interrupt service routine. Then once we finish, we restore the status of the CPU, load the program counter with the return address, let's say, then we resume the normal execution. Okay. So this is very typical. These steps are almost the same for all processors. However, the details of each step is different. For example, in our microcontroller, this step of saving the CPU status in the stack is done automatically. Restoring the values is done automatically. However, in some other microcontrollers, saving the CPU status, in other words, the registers, is not done automatically when we start to service some interrupt request. One thing that also varies between microcontrollers or CPUs is resolving the starting address of the interrupt service routine, or knowing the starting address of the interrupt service routine. And there are many ways, different ways to do that, depending on the microcontroller or the CPU that we work with. So the methods for determining the interrupt vector address, some microcontrollers, they have a predefined location. For example, they say source number 1, its interrupt service routine has to be loaded at this address. Interrupt source 2 has its interrupt service routine loaded at this address, and so on. So this is found in some microcontrollers, such as the PIC and the 8051 microcontrollers. Another approach which we have in the HCS12 microcontrollers is fetching the interrupt address from a predefined memory location. So there is a predefined memory location or locations for each interrupt source that are enough to store a memory address, and this memory address is basically the interrupt service routine address, as we will see next time. So for every interrupt source possible in the HCS12, we will see that in memory there are specific fixed predefined locations, effectively 2 bytes, to hold a 16-bit address, which is basically the address of the interrupt service routine of this, or of this interrupt, associated with this interrupt, this interrupt source. Okay, so here in the first approach it's different. We simply fix the address of the interrupt service routine. So the interrupt service routine has to start at specific address. While in the other approach, no, we fix the address from which we pick the subroutine address. We load the subroutine, the interrupt service routine address, which is more dynamic, but of course it is more complex and takes more time to execute, because you need to go to memory, read 2 bytes, which represent the interrupt service routine address, and load them to the program counter in order to execute the interrupt service routine. However, in the first case, you simply, when an interrupt request arrives, you simply go to the address associated with this interrupt source and start executing. So it is faster, but this is more dynamic. The second approach is more dynamic. The third approach, I will not talk about it. It has something to do with additional hardware. You need to insert an additional hardware in order to coordinate the interrupt. Now, if I go up to put things formally, there is something called interrupt vector, which is basically the starting address of the interrupt service routine. So it is nothing new. Interrupt vector table, basically the table that contains the interrupt vectors or the addresses of the interrupt service routine. So that's why if you go here at number 2, fetching the vector from a predefined memory location, which means fetching the interrupt service routine address from predefined location. So interrupt vector table, basically it's the set of locations containing the interrupt vector addresses, or the interrupt addresses, simply the interrupt addresses. So I have less than 1 minute in this meeting. I'm not sure what's the problem, why it's doing that. So